Yeah, so I'll go through the Eclipse keywords which we need to use in gas for pseudo pressure options and how to include capillary number effect in Eclipse 100 and 300 and how to include this non-Darcy effects. And then I have one example from one of the previous study. So I'll go through how data we got and then how we included that. So first is the pseudo pressure option in Eclipse. If we want to activate, then how to do. So here, as we know, the pseudo pressure option, you have already discussed, Curtis, about this. So in Eclipse 100, we have to write this GPP under item 8 under well spec keyword. Well spec where we define the well, like the well name and where well is in which group it is associated, what is the location of well, I and j coordinates. And under item 8, we define this GPP option, then it will activate pseudo pressure option calculation. That's for the Eclipse 100. And well spec, we use one line for each well. So we have to use this GPP for each well. In Eclipse 300, we can use the same like whatever we do in Eclipse 100, GPP for item 8 under well spec. But there are two more keywords in Eclipse. There are two more keywords in Eclipse 300 in addition to this item 8 well spec.
It says or. Does it have to be and?
No, it's or. No, either we have to use this one pseudo press or well p icon or this one.
Either or.
Yeah.
Okay. Not both. Yeah.
Not both. So this is or. If we write pseudo press keyword once there is no associated data, then it will be applicable to all wells in the model. So the difference is that here in this case we have to specify GPP for all wells. Here only once.
Okay.
So there is no associated data, and then once you have this keyword, then it will always use GPP for all the wells. Okay. They have also one keyword in Eclipse 300, WP icon, and here also we can activate GPP option, but here we can give some more flexibility. Like if we give well p icon, if I want to use GPP option for well starting with well name, let us say A, for example, so we can give A star and then only give the GPP, and then it will use for all wells starting with A. So basically they have included WP icon. It's in between, I will say, pseudo press and well spec. Well spec, we have to give one line for each well. Pseudo press, we have give only once, and then it will applicable for all wells. And then WP icon, you can give for a group of wells. There are some more options in well p icon where you can also define some other parameters.
Can those parameters that can be defined there not be defined in the pseudo press and GPP?
Yeah, so there are some parameters in here it can be defined which cannot be defined in well spec or pseudo press, but for that we have additional keyword p icon. Okay. So that I will go through. So basically well p icon is in between pseudo press and there is one keyword known as WP icon. Okay. So mostly we are running Eclipse 300. Most common is just to give pseudo press one line, and then it will activate pseudo pressure option for all the wells. Only we have to take care that pseudo press should be defined before defining any well. But once you go through the keyword, then it clearly says that, okay, you have to enter this keyword before defining any well. So if you have defined a well, and after that, if you are giving pseudo press, then it will only take pseudo pressure for the wells which are coming after pseudo press. So what Eclipse does, once we activate a GPP option, then it makes a table, pseudo pressure table, and then it have on that integral, the way we saw that from pressure like mobility, from reservoir pressure down to bottom hole flowing pressure, you have to make this. We see the graph, and then what we have to take different pressure points to make it like integral. So what will be the, maybe it should have, what will be the, like, how many pressure points we need to take to make that line? Like okay, data. We have to make this lambda mobility.
Do you want to draw it, or just okay? You need to use the mouse to move the. Just grab onto that. Keep it at the next page.
So like the integral we had, if we take this
eraser. Just a pen.
So if this one, for example, bottom hole flowing pressure, and here it was coming somewhere, and then this is the dew point
P star.
Dew point pressure, and then it is the reservoir pressure. So how many points to take to make this graph or this curve? So what will happen? So in that particular, so let us say we are having between PWF and P dew point.
Alt tab.
Yeah. Right. What was that?
Just you can go down to the PowerPoint symbol there. That should bring
No,
it.
I want to be here only, but mouse.
Oh, to bring it, you mean to bring the page up?
No, just I want to look at these points. Mouse is not visible here now.
Oh, okay.
Yeah, it's just very small.
Yeah, it's very small.
Here. Okay, then I can just do that. I'm not sure that we can do anything with.
Making an eraser, then that's a bigger symbol.
Yeah, if you want to just point.
Bigger on the screen.
Yeah, because Bilal he saw something.
But that was in the PowerPoint.
Oh,
It's specific to PowerPoint, I think.
so here, like if we want that we have these points every one at 14.7 psi, and then we can define what we want to have every 50 psi.
Yeah.
So these are the control is given by keyword P icon.
Let's just try this one instead. It's the little. Okay,
But isn't that okay?
Yeah, it shows bigger in the screen, in the WebEx screen.
So this P icon keyword is available for both Eclipse 100 and 300. And here we have to give different numbers. Like the first number is saying 14.7. Default is 4 atmosphere. But if we say that 14.7 in fill unit, so it will take that point every 14.7 psi for making this pseudo pressure integral calculation. This is a below dew point. What should be the delta P? It's 14.7 between reservoir pressure and dew point. This is a type of damping factor, and similarly we have other parameters here. So this PI count we have to give and it is applicable for all the wells. We can also give this WPI count, but it's only available in Eclipse 300. And here we can see both. We can give the well number, well name, or some star. And then here we can also set that do we want the GPP option activation or not. And then we can also have this all the numbers we had in PI count. So basically, WPI count is a combination of PI count and pseudo press. So there are two ways. Either we can give pseudo press and PI count in Eclipse 300, or we can give WPI count, and then here we can say yes, we want GPP option, and then we can give the parameters option.
So if the first just says asterisk instead of P asterisk,
then it will take for all the
all
wells.
wells.
Yeah.
Okay.
So if we give PI count, we don't need to give WPI count, then we don't need to give PI count and pseudo press.
No.
Here there is in the item number here 4 in the PI count and 6 in WPI count. If we want to have include the effect of capillary number, we have to say yes. But I'll go that in the next slide. Then that will activate
I think
pseudo.
there was a question from Islam.
P star should mean all producers.
Yeah, well,
Let's
all
see.
wells that begin with P.
Yeah,
You
so
say
P
that P stars if it means all producers. It's supposed to mean all producers.
yeah, this for all the wells, yeah, for all producers, yeah.
Mm.
It is the wildcat, so we can give.
I mean, a producer well name can start with G.
Then
So
it
then you
will
have
be-
to start the GS star.
Yeah.
So producer means it's not the producer, it's maybe the
Yeah.
name, yeah. It's the first word of the well.
Yeah. So this P star means that any well that starts
Starts
with a
with
P will be taken, and by default, generally you name the producers P, but not necessarily
Yeah, so we have the well W1, W2, then
Yeah.
we can say W star.
W star.
So
Okay.
maybe it's better to have been given like A star, then it was more less confusion, I think.
Okay.
So P is not meaning here the producer. It means that the well is
Any
starting
well
with the,
starting with P.
yeah.
Okay.
So how to activate capillary number effect? So here to activate capillary number effect, we have to use this keyword velocity dependent relative permeability. This is well depth in Eclipse 300. And there are two models
It's not available.
in Eclipse 100.
It's not available at all in Eclipse 100.
Yeah, so that's why we are modeling capillary number effects in Eclipse 300. So there are two models for capillary number effects. One is the Harriot-Ward, and second is the Whitson-Feynman. And Eclipse 300, they also say that alternative model. So if we say in well depth, item number 1 and 2 activates this Harriot-Ward model. To activate Whitson-Feynman model, we have to go in item number 5 under well depth, velocity dependent relative permeability. And item number 5, we can give either 0, 1, and 2, but we have to enter 2. So under keyword well depth, item number 5, we have to write 2. Yesterday there was some one question about 1 and 2 and combining here. So this I have taken from Eclipse manual. Well depth under 5, it is saying that this item controls whether an alternative model for capillary number effect near wellbore flow in gas condensate reservoir is active for gas or gas oil phases. This model is activated for gas phase only by setting item number 1. So if under 5, if we write 1, then it will only activate for the gas phase. But if we want to activate for both oil and gas phases, then we have to write 2. But we have never tried this, use this number 1. But here, I think somebody, it was Osman or somebody asked that what is the 1 and item number 2. So why we use this item number 2 in 5? Because this is the original one, and here R is defined as KRG by KR. And it has only 2 parameters. Somehow, if there is some, it's not clear why they are. If we go in the manual under well depth, they are saying that if you write 1, then it will only activate for gas phase. But if we go deep in the manual, they are giving some other calculations there. And then here they are combining both Whitson-Fewang model and Heriot-Watt. And that's why they are saying that if we use under 5, if you give 1, then at the last it's saying that somewhere it goes to, yeah. So total parameters going from 2 to 5. So they are also taking some parameters from Heriot-Watt model. We have never tried, we have never recommended using 1 under item number 5. Okay. So once we have selected which model to use, like if we select the Heriot-Watt model to use, then what parameters should be for that model? Those are given by keywords VDKRG and VDKRO. Velocity dependent gas relative permeability and velocity dependent oil relative permeability. If we select this alternative model, or Whitson-Fewang model, then the parameters, 2 parameters for this model are defined by keyword VDKRGC. And once we are activating capillary number effect, and we want to include that in the GPP, we have to just go in the PI count or WPI count keyword, and we have to say, yes, we want capillary number effect in GPP calculation. In Heriot-Watt model, there are a total 4 plus 4, 8 parameters, and they don't have any default value for that. But in alternative model, there are only 2 parameters, and these parameters can be obtained from lab experiment, or there are also some default values for this, but there is no default value for this Heriot-Watt model parameter. Now going to this non-Darcy flow effects in Eclipse 300. So for that, we have to go in the same keyword well depth and item number 3 and 4. Item number 3 is non-Darcy effect in oil phase, and item number 4 is non-Darcy effect in the gas phase. And like item number 3, we can give 0, 1, or 2. 0 means non-Darcy flow effect. 1 means there is a non-Darcy flow effect, and use this model 1 for beta parameter. If you are using model number 2, then it will use this equation for the beta. We have seen that generally model number 2 is, we have tried 1 and 2, and we have always seen that model number 2 is better. Consistent.
Better in fitting that real data.
real data, and I think we have also did some consistency check, oscillation running, and we always found this model number 2 gives always better. So what in the model number 2, this beta phase is beta dp, sp, and this one. So dp is this single phase gas beta. So if you have done like a single phase gas permeability experiment, then we get beta from fitting of those data. And in the literature, also, if we have two phases, like if we have, of course, there will be initial water saturation, and in region 2, we have both immobile oil phase and mobile gas phase. And we do experiment, we do gas permeability measurement for region 2, and we have seen that beta in that experiment in presence of immobile oil is different than whatever we have beta single phase without oil, immobile oil. And if you want to model that, then we have to use this, generally we use this equation. We know this BDP with non-Darcy beta from a single phase gas in absence of oil phase. And then we know the beta in presence of oil phase. And then we try to fit and get this relation. So generally we fit with this parameter CP. And here SP is showing phase saturation. So for the gas phase, SP, the gas saturation is divided by 1 minus SWC. Generally, we keep DP like a parameter D equal to 0. So basically, most of the time we have seen that this B for the phase, for the multi-phase, equal to B for the dry single phase gas time this SPCP, and we try to change this parameter CP to match the lab measure data.
So saying on the definition of SP to the right, what does it mean SP to the power of 3P?
And it's not the power, it's saying the like three phase. If we have the oil,
so this
gas,
this is just the actual three-phase saturation. I mean, what other kind of saturation is there?
Like what kind of saturation?
I mean, it's just the saturation of that phase.
Yes. So here, like it's saying the saturation of gas phase in case of there is three phase in the core: oil, water, and gas.
But it's only the phase of
gas.
Yeah. So it doesn't matter if there's one or two other phases. Okay. Okay. That's strange. Okay.
Maybe I should have written like here, but since I took simply copy and paste for the manual, so I think it will more clear if I should have written SG equal to SC divided by 1 minus HW.
Right. Okay. And then the capital K is absolute permeability?
Absolute permeability, and then this is the relative permeability.
Oh, so VP, what is VP?
Relative permeability of the gas.
What's the V?
VM.
Is that the velocity corrected KR?
Maybe I have to go and see what
the one that capillary number corrected, maybe?
No, I think this is a type of relative permeability.
Okay, that's strange. Okay.
But generally, we have found that if we change the CP, we tried, so this always, and in the literature also, I think mostly they refer SG equal to SG divided by SW, and then if you change some saturation exponent. So the how to enter these parameters A, B, C, and D. So those model parameters we can define under the keyword VDKRG and VDKRO. So we have to find these all A, B, C, D, and BDP from the live experiment. So here just I'm showing one result from one of the project based on the lab experiment. So let us say we have done the experiment and we have developed this immiscible curve, which is raw curve, and for this particular case, this KRG at KGK1 equal to 0.05. And based on the data fitting, we got this alpha parameter 2054 and exponent 0.74 for Wilson-Febvre number model. And then parameter for the non-Darcy flow, beta parameter single phase gas is 2.79 e to the 2.7 E9. And then based on the beta measurement in presence of immobile oil, after matching that, we got saturation exponent minus 2.15. Minus 2.15, which is, I mean here, CP. So if we have got this data, then how to enter that in Eclipse 300? Going again here. So this is showing an example to activate pseudo pressure option. We have to write this well spec and go in item number 8. 1, 2, 3, 4, 5, 6, 7, and 8. We have to write GPP. So once we write GPP here, it activates the pseudo pressure option. And then we have to go in the activate capillary number effect and non-Darcy flow effect. We have to go in this keyword VLDP depth, and we have to go on item number 5, and we have to write 2 to activate alternative model and activate for both oil and gas phase. This 4, 1, 2, 3, 4. Item number 4, we are giving 2. It means we are activating a non-Darcy flow effect for the gas phase and using model number 2. Then to give the Wilson-Febvre model parameters, then we go VD-KRGC and we write 0.74 and 2054, whatever we got here, 2054 and 0.74. We just write here. Then whatever we got these parameters for the beta, 2.7, e to the 9 and minus 2.15. We write, we come here, VD-KRG, and then this is the value we have to write, minus 2.15. And this beta we get per meter, and then we have to convert in the unit they use in Eclipse, and it comes 26.2. And how to convert from meter to this unit, it's already given in Eclipse manual. And then we have to also use this PICON keyword, and we have to write yes in under item number 4. And these parameters, other parameters, we can keep default. But generally, we have found that if we get write this one, 1 atmosphere instead of 4 atmosphere for the integral table, then we get consistent result and there is no problem. And of course, we have to enter this base curve or immiscible curve, raw curve, and then we just HGOF, and then we define and write here. Yeah. Any question? Yeah, comment?
The other numbers you have on the PICOM, the 14.7, 14.7, those are the integral DP increments below the dew point and above the dew point.
Yes.
So that's clear. And the 0.5 is some kind of a damping factor.
Yeah.
Is that explained in the manual, or is it important, or is 0.5 the default, or?
It is explained in the manual that what are the damping factors. If you start seeing the oscillation
Oscillations in
the
what?
simulation calculation,
Oscillations in GOR or oscillations in?
it starts giving warning that okay, you have to change this damping parameter, and it starts taking more time.
Okay. And it actually will give you a warning that this is the problem, or not?
Either it will give, generally we see the oscillation, it starts taking time.
Okay.
So what we have found, this combination generally we use based on the work we did long time back.
Okay.
And then we found that if we use this combination in coordination with these Eclipse people at that time,
yeah,
then we found that this gives us a reasonable result.
So I think what's important here to make a comment, at least if I were you guys going to be using this, these numbers here are Singh's, which is, Whitson's recommendations for the default parameters. And don't put an asterisk there, because what it gives you is the default is non-optimal. We've, through experience and working with Schlumberger,
yeah,
these are the numbers that probably should be default.
That's correct.
Okay.
Yeah. So this is based on our
They're
experience.
not just an example. They're not just a random example. These are the default recommendations.
Yes.
Right?
Yeah.
Okay. Okay. And that's by us, not by Schlumberger. That's
yeah. So they have some different default, but this is based on our experience.
okay. Now, anybody else in the participation who's used these options found something different? Want to share your experience?
We're using this
Hello?
option, but use more or less this thing.
It's a little hard to hear you. I'm sorry.
Their model.
It's still a little bit weak.
Samir, your sound is very weak. So you need to if you can try to get closer to the microphone when you speak.
No, I'm just saying that we're using the same.
The same numbers in the PI con?
You have to write the question.
He says, sorry, I have connection problems.
Okay.
Because the default here is 4 atmosphere for the first, and for the second is the 10 atmosphere.
Yeah.
You would think it would be better if you had like a non-Cartesian reading, because of the way it increases with.
Yeah, but you don't have that option.
Yeah.
So,
We use the same models with similar numbers for well depth.
VELDEP.
Yeah, the well depth 00022.
Yeah. So
What about the numbers in the PI con? Whether the numbers that other people have used or found that were required to avoid oscillations, to get numbers that, because if you reduce the first two numbers, as you reduce them, you should get a converged solution. I mean, you get more resolution in how you integrate that, right? Yeah. So.
It's like a tuning parameter, we can say. Like if you're doing the simulation, then delta t, but it's not for the delta t, it's like for getting this correct integral.
Yeah, but if you, there's probably no gain to go to 2 psi.
No.
So, okay, but 60 psi and 150 psi for those first two parameters is not enough resolution in your experience. Okay.
Yeah. So here was that comment was that using the similar things for well depth keyword. Yeah, and this should be used because we have got this model number 2 based on our experience during testing that beta model 2 should be used.
Model 2 is this
This here. give
Okay.
this model.
Yeah. Okay. And the DP, the exponent DP, where do you see that being input?
Uh,
No, in the example.
in the exam, here, if you go in the example, this is for the
Default.
A, B, and this one is for C, and this one is for the D.
Okay.
So we have the default. Default is 0.
Is 0. That's what I was thinking.
Yeah. So all the defaults, if we don't write anything, then all 0 means no effect.
Okay. Yeah, 'cause
Something could
that's-
be 0 equal to 1.
Yeah, that makes sense. It seems strange that you had the effective permeability there. So, okay.
I asked Samir about this PI con, and he said he doesn't remember that,
No. Okay.
what they use in the model. In their model.
All right.
So I
Good.
think that way. This is a snapshot. All keywords are here.
Yeah.
So if we are going to a gas condensate, simulate gas condensate reservoir with GPP option, capillary number and beta. So these are all keywords we can use.
So the laboratory data that you spend $250,000 getting is going to give you basically the numbers 0.74, 2054, the minus 2.15, the 26.2,
And
and
then,
this curve here.
yes.
Yeah.
So this is the output from our
Yeah.
live experiment.
Yeah.
Okay, Curtis.
Great.
Thanks.
Thanks so much, Singh. Appreciate it.
Thank you, Zane.
Okay. Okay. Okay, then I think that was great. I think for those who are trying to use these options, having some good defaults takes you a long way. Forsheimer equation for oil phase. So, good question. So that first is that this Forsheimer equation as Darcy is not phase dependent. Okay, so we're talking single phase, right? So you basically the equation is supposed to apply to any single phase. That's the first reason. Now the question is what Muscat actually showed way back in I think it was the 30s, maybe the 40s, is that if you plot a Reynolds number, a type of Reynolds number, which you guys are going to have to help define. And if you look at basically the, laminar flow is something like this. This is laminar flow for pipe. And then it transitions into this turbulent flow here. Right? This is related to the pressure drop. It's not exactly the pressure drop, but and the Reynolds number is, help me, pipe flow people. You got density, viscosity, and velocity, I think. So presumably velocity is on top. Actually, I'll show you
You can write it
let me just,
as density,
okay. Yeah.
and U,
Density.
slow U,
Density, velocity.
Density,
and the
velocity, and the
and then
diameter of the
D,
pipe.
which is the diameter of the tube. And
Divided by,
viscosity. Times diameter of the tube
That's the diameter.
divided by viscosity.
okay, there we go. Okay, and so what Muscat did, he took flow through porous media data. He didn't say if it was gas or oil, though it was gas. And basically he defined the diameter was the average, if I remember right, particle diameter from a sieving exercise. They basically crush the sand and they sieve into different sizes. It's the average, some kind of average pore diameter. And then he just did flow tests with gas, but it didn't matter. It was a single phase fluid at certain velocities, and basically shows that all this data. I was going to go find you the actual plot. Look like this because it's an interesting. People are not familiar with it. Okay. So this is delta P, and it's divided by velocity squared. And this looks just like a pipe flow friction fracture. So these are for different rocks, unconsolidated sand. So basically, where it's got this straight line slope of -1, it's Darcy flow, and then it starts bending over, and that's the Forsheimer equation. It can be fit by other equations as well, but I think the Reynolds number where you start getting this deviation, I think he says is somewhere between 1 and 10, which you can kind of see from this. I think he gives in the discussion in the text, this is just the figure. So you can kind of see the deviation starting between a Reynolds number of 1 and 10. Okay, so the first reason is that, so basically this is this transition here from Darcy into Forsheimer is basically Forsheimer's all the way here. This here is somewhere between 1 and 10. And so that's basically the second reason. So if you have an oil that's flowing, it's got a density and pore size distribution and viscosity and so forth, where you depart from this -1 slope, then Forsheimer equation applies. And what's interesting, in a paper in 1970, I'm not sure when, Mike Fetkovich, again, he published data from the initial well tests of the Ekofisk field. And basically, from that paper, I'll show you that paper. It's called the isochronal testing, which is normally associated with gas. Why would you do an isochronal test for an oil well? He wrote an entire paper about why you would do it, and the Ekofisk example was why. And he showed that most of the tests deviated from Darcy's law, according to the Forsheimer type equation. And because that was the standard for those Ekofisk tests, let's see here. See here also he talks about treating condensates. But let's see here. I'm getting off track. Let's see if I can find it. Reynolds. There we go. Okay, so let's see. Analyses performed on buildups obtained all 4 flow tests. The skin effect calculated. Non-Darcy coefficient, he actually gives the D, was obtained. It was a partially penetrated well. So basically, he said a further verification of non-Darcy flow in this well was made by checking the Reynolds number. Reynolds number of 8 was obtained for the well under its flowing condition of 3,000 barrels per day. So he actually computed that. A grain size of 0.5 millimeter, according to Muscat, exactly the figure I was just showing. So the reason that you would potentially want to use it is that these guys are saying there's no reason not to use it. Okay, so if you have oil viscosity of Ecofisk was 0.2, so it's a light oil, low viscosity oil, and there are experimental evidence in the laboratory from Muscat and from the field, Fetkovich, that basically says, yeah, light oil wells can in fact flow at velocities that deviate from Darcy law. So that's the kind of long answer to it. So that paper here was classic. I think it was 73. Yeah. Okay, is that the and the thing is that remember in the calculations that Bob Mott made in this example, in region 1, by the time you get to the wellbore, even for that lean condensate, what was it? 18 of the 24 stock tank barrels were flowing in the oil phase. And the other 8 were being carried in solution in the gas, which means that the velocity of the oil was also significant at the wellbore because of the region 1. So you're going to get pretty high velocities both for the oil phase and the gas phase. Now, the Reynolds number, of course, for the oil phase will be, the density will be higher, the viscosity will be lower, but the viscosities, let's see, the ratio for these really light condensates is not, for the condensate phase, is not that different than from a high pressure gas phase. So you don't get these huge contrasts. The rho over mu for the condensate is not that different than for the gas. And the velocities are similar in region 1, particularly at the wellbore. So, you could get the effect for both phases. It's an interesting paper. Okay.